Hi, myself Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, we are going to say about the transmission electron microscope, which is a characterization technique. So, TEM means transmission electron microscope. Transmission electron microscope. So, this transmission electron microscope, TEM, also known as conventional transmission electron microscope. Conventional transmission electron microscope, that is CTEM. CTEM. So this was invented in 1933 by Max Knoll and Ernest Ruska. So Max Knoll and Ernest Ruska invented this transmission electron microscope in 1933 in Berlin. In transmission electron microscope, electrons are accelerated from 10 kilovolts to 1 mega electron volts projected onto a thin specimen which have the thickness less than the 200 nanometers. So, in this transmission electron microscope, the electrons are accelerated with some potential difference, that is 10 kilo electron volts to 1 mega electron volts, and these electrons are projected onto a thin specimen, so which the specimen thickness is less than the 200 nanometers. So, the electron beam is projected onto the specimen by means of condenser lens system and penetrates the sample either by deflected or non-deflected. So there is a electron beam of electrons which are focused on the specimen. So specimen is nothing but a crystalline material with some thickness that is less than 200 nanometers. The specimen which have the less than 200 nanometers. Thus, the specimen thickness T is equals to thickness T is less than 200 nanometers. So, how we are projecting this electron beam onto the specimen? By using the condenser lens. Here we are using condenser lens system. So electron beam is projected onto the specimen by means of condenser lens system and penetrates the sample thickness either deflected or non-deflected depending upon the thickness and the arrangements wherein the size, that is a crystal thickness, it will be deflected or undeflected. It makes diffraction pattern. During the passage of electrons through the specimen, there are two types of scatterings which is experienced by the electrons. One is elastic scattering and inelastic scattering. So, when coming to the elastic scattering, it involves no energy loss. When the electron hits the target or sample, there is no energy loss. Energy loss takes place and gives rise to diffraction pattern. So, in elastic scattering, there is no energy loss and it gives diffraction pattern. Where in the case of inelastic scattered, so the inelastic scattered electrons are the electrons which lose part of their energy, through the interactions between the electrons and the specimen. So the electrons loses some of its energy or all of its energy. So during the passage of electrons through the specimen, electrons passing through the specimen, so it encounters two types of scatterings. One is elastic, another one is inelastic. So in elastic, no energy loss, so that it gives diffraction pattern. Where in the case of inelastic scattering, so it loses part of their energy. So energy loss takes place. Energy loss takes place between the interaction of electrons and the specimen. So in elastic scattered electrons, the electrons loses part of their energy through the interactions between the electrons and the specimen. So electron loses some of its energy or all of its energy in this case. So when coming to the transmission electron microscope, so how the TEM works? Working of transmission electron microscope. So here we need an electron beam. We need an electron beam, so that we use electron gun to produce monochromatic beam of electrons. So the electron gun produces a stream of monochromatic electrons. So this stream of monochromatic electrons is focused to a small coherent beam by the first and second lenses, condenser lenses. The condenser aperture knocks off high angle electrons. So here there is an electron gun. So this electron gun produces monochromatic electrons, stream of monochromatic electrons. So these electrons are in all the directions, so that to focus this stream of electrons which are coming from the electron gun, we use condenser lenses. That is, first and second condenser lenses are used to make focus of this stream of electrons. So the condenser aperture, here it is the condenser aperture. This aperture, what it do? So this condenser aperture knocks off high angle electrons. So high angle of electrons does not focus onto the particular area which we need to target. So that that high angle electrons be blocked by this condenser aperture. Then the beam strikes the specimen. So after this condenser aperture, there is a sample. So this sample is the specimen which we are talking about. So after the condenser aperture, there is a sample. There is a sample which is a specimen. So that the beam strikes the specimen. So then when it hits the specimen, the transmitted portion is focused by the objective lens into an image. So this objective lens, that is transmitted portion. So the electron beams strikes the sample. So when it strikes, it may encounters deflections or undeflections, whatever that. So transmitted portion that whichever is transmitted, so that transmitted portion is focused by the objective lens into an image. So the objective aperture enhances the contrast by blocking out high angle diffracted electrons. This objective aperture enhances the contrast by blocking out high angle diffracted electrons. Then a selected area aperture. Selected area aperture. It enables to examine the periodic diffraction of electrons by an ordered arrangement of atoms in the sample. So, selected area. So, wherever we want to examine the crystal, so we can arrange periodically the diffraction of electrons by this aperture, selected area aperture. So, selected area aperture enables us to examine the periodic diffraction of electrons by an ordered arrangement of atoms in the sample. Intermediate and projector lenses enlarge the image. These two, first intermediate and second intermediate lenses, then projector lenses, these are used to enlarge the image. Enlarge the image. So the beam strikes the phosphor screen and image is formed on the screen. So the dark area of the image represents the thicker and denser sample areas. Since these areas transmit lesser electrons, the brighter areas of the image represents thinner or lesser dense sample areas, since these areas transmit more electrons. So here it can be seen clearly. It is electron gun. So which produces beam of electrons. Monochromatic beam of electrons that is focused on these two condenser lenses. First one is first condenser lens and then second condenser lens. This condenser lens is made to focus. That is, it blocks or knocks off, it blocks the high angle electrons. High angle electrons. Then it focused and strikes the sample. Electron beam made focused onto the sample. So when it focused on the sample, it may deflected or diffracted, deflected or undeflected. So the transmitted portion of electrons we passed or focused on the objective lens. So this made to focus the image and knocks off the high angles of electron beam here, and we use this objective lens and objective aperture. Then we have a selected area aperture. So this selected area aperture is used to know about the particular area which ordered crystal we need to know. The selected area aperture So periodic diffraction of electrons by ordered arrangement we can examine by using this selected area aperture. And then intermediate and then projector lens is used to enlarge the image. Then it will be focused on the phosphor, which is a fluorescent screen. Or phosphor screen. So electron gun produces electron beams that will be focused on the condenser lenses. These condenser lenses are used to focus, not to be have high angles. So it focused to fall on particular area, and then it falls on the condenser aperture. So here the high angle electron beams are knocked off. Then it strikes the specimen. So after striking the specimen, the transmitted portion focused by the objective lens into an image, and then objective aperture, it enhances the contrast by blocking high angle electrons. Then by using this first intermediate and second intermediate projector lens, we can enhance the image and can be seen on the screen, which is a phosphor screen or fluorescent screen. When taking thin specimen, the interaction of electron with the specimen will be unscattered electrons, elastically scattered electrons, or inelastically scattered electrons. How they are appear on the screen. So these unscattered electrons transmitted through a thin specimen without any interaction occurring inside the specimen. No interaction takes place inside the specimen when these electrons are transmitted through the specimen. So the intensity of transmitted and scattered electrons is inversely proportional to the thickness of the specimen. So thicker areas of the specimen appear darker than the thinner areas, because these unscattered electrons does not affect, or they do not interact with the atoms inside the specimen, so that electrons is inversely proportional to the thickness of the specimen, so that thicker areas of specimen will be appear darker than the thinner areas. In elastically scattered electrons, the electrons are scattered by atoms in the specimen without loss of energy. So these scattered electrons are then transmitted through the remaining portions of the specimen. So the scattered electrons follows Bragg law as n lambda is equals to 2d sine theta. So the scattered electrons, that is the Bragg's law, is n lambda is equals to 2d sine theta. So where n is the order of diffraction, lambda is the wavelength, and d is the wavelength or interplanar spacing. So by collecting the scattered electrons at different angles, we may get the information about the orientation, atomic arrangement, and the phases present in the crystal. And coming to the inelastically scattered electrons, these inelastically scattered electrons interacts with the specimen and lost their energy, some of the energy. So these are the electrons that interacts with the specimen atoms in an inelastic manner, loses its energy. Then they transmitted through the remaining portion of the specimen. The inelastic loss of energy is characteristic of the element that have interacted with. These energies are unique to bond of each element. Hence, this can be used to extract both the compositional and bonding formation. So, this is the image which is taken by the TEM, transmission electron microscope. So, this image gives the carbon nanotubes coated with a thin polymer layer which have the size of 500 nanometers. So, advantages. Selected area diffraction offers a unique capability to determine the crystal structure of individual nanomaterials such as nanocrystals and nanorods, and the crystal structure of different parts of the sample. Selected area diffraction patterns are often used to determine the Bravais lattices and the lattice parameters of crystalline materials by the same procedure used in the diffraction of X-rays. TEM can also be used to determine the melting point of nanocrystals. An electron beam is used to heat up the nanocrystals, and the melting points are decided by the disappearance of a diffracted pattern. So this TEM used to measure the mechanical and electrical properties of individual nanowires and nanotubes. So, and also there is much more advantages of this TEM. So, it's a highest magnification up to the order of micron, and its ability to provide both image and diffraction information from a single sample. So using this TEM, we can get the information of morphology, crystallographic information, and then compositional information. So morphology in sense, the size, the shape, and arrangement of particles as well as their relationship to one another on the scale of atomic diameter. Crystallographic information, the arrangement of atoms can be known in the specimen and their detection of atomic scale defects for a few nanometers in diameters. Compositional information can be obtained, that is the elements and compounds of the sample is composed of and their relative ratios. So what are the limitations of transmission electron microscope? So TEM has some limitations. Samples must be electron transparent, which means that sample thickness must be 100 nanometers or less than that. TEM samples are also vulnerable to radiation damage from the electron beam. To counter this, fragile samples such as biological macromolecules can be pre-treated by instant freezing and analyzed by cryo transmission electron microscope. So the references are Engineering Physics by K. Tyagarajan, McGraw Education India Private Limited, New Delhi. A textbook of Engineering Physics by a textbook of Engineering Physics by M.N. Avadhanulu, P.G. Kshesagar, S. Chand and Company, New Delhi. Engineering Physics by Dr. M. Armugam, Anuradha Publications, Chennai, 617. Engineering Physics, P.K. Palanisamy, 4th edition, SciTech Publications, India Private Limited, Chennai, 617. Engineering Physics by Dr. K. Vijay Kumar, S. Chand and Company, New Delhi. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.